In this video, we'll go over how we can determine co-elutions within a whole batch of injections using visualizations and base peak mass. And we'll go over more details about how visualizations work and what you can achieve with them. So what you see right now is a big shoulder next to our peak of interest. If the co-elution is very large, like in this case, it's possible that the most prevailing mass within the peak is going to be not of the compound of interest, but of the co-eluted one. If that's the case, such co-elutions can be spotted very easily simply by inspecting the peak's BPM, meaning base peak mass, and comparing it with the expected molecular weight. If they're different, we clearly got a co-elution. Let's go to the batch level because we want to leverage visualizations in order to spot all such cases within a batch. Here, I've already prepared a chart that shows the difference between peak BPM and exact molecular weight of our compounds. I've already filtered out all the good peaks and left only bad ones. So if we select all these points, we can see that there are 17 injections where peak BPM is not the same as expected molecular weight. If you're using our demo instance, you can simply apply this template into your batch and see it right away. But I'm going to go through the details of how you can create such charts yourself. So first of all, we go to Visualize menu item or simply press V as a shortcut. And here we can create a table with injections as rows or peaks as rows. In this case, I choose peaks as rows because I'm mostly concerned with the peaks and their health. Now we can select which columns to add. I'll leave injection name checked, but I'm mostly interested in exact molecular weight of our peaks and their base, which for mass spec is a BPM. Just to add more context to the information, I will add the alias of the substance. And also, for reasons I will go into later, we will add the chromatogram name. The rest of the information is not relevant to this chart, so I will not include these columns. Here's our data. As you can see in the first row, the EMW and the base differ by 1, which is expected since the compound was ionized by H+. In some other rows, the values are quite different. And in order to see the difference more clearly, I'll add a calculated column and subtract one value from another. I'll call the column observed minus expected m over z, and we'll enter the mathematical expression. We can see the newly created column that holds the difference between the two others. Now I'd like to plot this difference. I'll choose it as one of the axes. As you can see, there are plenty of values that are close to 0. This is our 1 Dalton difference because of the hydrogen. But there are plenty of other values that are different. Seems like there are too many of them, so something must be wrong. Now it's going to be clear why we added chromatogram name as one of the columns. See, when Pixel calculates a base for the peak, mass spec peaks will have their base peak mass as the value, but UV peaks. The most abundant signal in such peaks is called lambda max. It's the wavelength at which the compound absorbs light the most. And of course, it has nothing to do with the molecular weight of the compound. So these rows mislead us and we need to filter them out. Just to make it prettier, I'll rename the column to just chromatogram. And then we'll be using it in the filtering, where we can also enter an expression which has to evaluate to true in order to be included in the table. So I want my chromatogram column to contain this phrase in order to be included in the table. And this will effectively filter out all the UV chromatograms. There you go, no UV anymore, just mass spec. If we return back to the chart now, we'll see that there are fewer points. We're pretty much done now, but to simplify the picture, let's remove those points that don't look like co-elution. For this, we first want to add a column that clearly states whether the value is expected or not. We'll copy the column name with the difference between observed and expected masses, and we'll check if it's within the expected range. If so, the column will contain true, otherwise it's false. Whoops! Right now it's the opposite of what we need. I need to invert the expression. As you can see, wherever the difference is too large, we have false. What's left is to use this column in the filtering expression. Again, we'll copy the column name and we'll include it in this expression. So both conditions will have to be met. The chromatogram contains words MSSQD and the column is not within the range. The rest of the values are going to be filtered out. And now we're left with a very clean picture that only points to the chromatograms that contain peaks that are co-eluted according to our algorithm. Just to make it prettier, we can color those points by substance, but overall, this is not required. And just to make sure we've done everything correctly, we'll go through chromatograms, and we'll see that this is a co-elution, that is a co-elution, and all of the cases highlighted are actually co-elutions. That's it. I hope you will appreciate the abilities that visualizations give you and will use them to optimize your workflows.